welcome to the Imaging One World series talk. So this is a series of talks that we have every week covering different aspects of microscopy and applied microscopy. And we've actually got quite a busy plan for the next coming months, actually most of the way through to the summer already. So hopefully you can come back and enjoy some of the other talks in the near future. I'll hand over to Curti for today's introduction.
Yeah, it's great pleasure to introduce Bene. I know Bene from last 2-3 years. We met in Cambridge during Imaging One World and next Imaging. And since then, I have worked with Bene on a lot of things like applying for this another conference which is called Symposium. So he's one of the best emerging scientists I can say. So Benedict started his career as an electrical engineer, and now he's in Rainer Heinzmann lab, and I guess we can call him a full physicist now. So one of the very interesting things about Bene is that starting in his PhD itself, he's pushing for these open source tools. Some of you might have heard about UC2, which is I think a very exciting thing coming up, especially if you think in terms of high school or in bachelor's or undergrads where such tools can be of great use. So I'm really looking forward to the talk from Bene, and hopefully he can have a long-lasting impact on microscopy.
Wow, that was a nice introduction. Thank you very much. Yeah, and also thank you very much for giving me the chance to talk about our recent progress in open science and open source tools. So the title, of course, is The Power in Your Pocket, because everything or most of it is based on cell phones as very powerful imaging devices. Nevertheless, I'll divide it in a few different topics. I would like to tell you why open science is so awesome and what you can do with your cell phone in terms of single molecular localization microscopy, and how you can use this new type of cube in your research very soon. Yeah, let's directly dive in. Well, everything, of course, is about microscopy today. For those who do not know where we are coming from, so I'm still PhD student in Rainer Heinzmann's lab in Jena, center of Germany, and the place where this fancy formula comes from, and the place where all the cool microscopes come from, of course. That's our work group. And well, to give a brief overview about macroscopy, well, it started somewhere microscopic. Then there were lots of very nice things happening: phase contrast, single molecular localization, which we heard, for example, last week from Holbein lab. And so we have been here somewhere with the smartphone microscopy. And yeah, so of course, the question is what's coming next? And well, let's start with a challenge. So I'm not quite sure what's the audience today, but I'm quite sure there are some microscopist people and of course also some biologists people. And well, imagine you have a crazy idea and you would like to save humanity. And then you of course need an experiment for live cell imaging. You need it for 2 weeks, and eventually it can get really, really dirty because spill might be involved. Well, then your boss says, nope, that's not possible at all because it's way too expensive. We cannot just destroy our stuff. Of course, your colleagues eventually also need your device once in a while. And then, of course, if you want to tune your device, it's not just possible because it's quite complex. So even though microscopy is a very interdisciplinary field, you need expertise in every subject. So that's something I would like to solve during the talk. And so one step we can use to at least raise another issue in science is, well, the issue itself is the reproduction crisis. So there have been numbers of studies claiming that there are many experiments not falsifiable. So that means you cannot really reproduce it. And that's mostly due to, well, complicated experiment design, cherry picking, also then keeping knowledge from others so that they cannot really use the manuscript as a kind of a recipe to cook it. And well, all in all, I think that's something I would like to really stress is that there's no real standard you can follow in order to perform the same experiment in your lab. Yeah, especially chemistry and physics are two disciplines where it's kind of severe. So 70%, one of the nature studies suggests that the experiments are not really reproducible. And well, some problems here. Also, the same study are taken out. So people claim that the code is not available. Of course, there's a solution. You can make the code available. Well, per experimental design, I suggested, yeah, make it standardized so that people can really just take it from the shelf, insert it onto your optical bench, for example, or a biological lab, and then just replicate it. Yeah, same with the data. Well, even though you have the code, you cannot really replicate the experimental results because the data is not available. So there's definitely a solution for that. And then, yeah, if it's, well, too difficult to replicate in terms of technical expertise, well, make it simple, of course. So, you know, all in all, well, maintain transparency and create a community around it. That's some findings, I think. And of course, we're the first tackling this problem. There's a solution. It's, in my opinion, it's called OpenScience. And there's, it's a summary of many different topics: open data, open access, open source, open research. And I think that's a field which is growing quite rapidly recently. And for example, if you have ever heard of Zenodo or like open source hardware, open access, Python, GitHub, and well, tons of other projects here worth mentioning, they all tackle this problem. Going from here, like the ordinary step of, well, performing research, where you start with an idea, you do the experiment, you conclude with a theory, or vice versa. Then in the end, you publish, and eventually after 2-3 years, you go to the public and say, oh, that's my finding. Well, that's, in my opinion, quite a, well, old school way of doing that, because everything's closed, and then the very last step, eventually you start discussing. So, and what we try to do is, like in every step, we try to go to the public and discuss it. And we found that it's really nice because you get lots of ideas back from the community, and also you do kind of a preprint or a peer review in every step, so you can always optimize. And especially, so what we learned, publishing stuff, for example, in open repositories like GitHub, and also asking the community like Twitter, really helps to improve the quality of the project in the end. So in the very last result, I mean, I think peer review is still necessary to really improve it. But then the very last step is like, okay, here's the result. And yeah, it's nice. And so what does it mean for optics? So going back to the poor biologist who needs a fancy microscope, and it's, well, we heard lots of things about STAT from Kirti recently. And so I just took a random figure from some random STAT microscope paper. And so just try to replicate this design here. That's hardly possible. Too many mirrors. The positions of the mirrors are not really mentioned anywhere. Also the brands and everything. So it says lambda half plate. I don't know which one is used here. So how could we solve that? So Kirti already mentioned that I started being an electrician. So, and when I did my apprenticeship like 12 years ago, one of my tasks was to make an LED blink. And so this is like the circuit for it. And well, you have to start with the circuit. You eventually create a PCB, you manufacture it, you solder it, you program that in the end. So then after 2-3 weeks, you really need to pray that it works in the end to just get a single LED to blink. And then right after I was done, there came this little thing, the Arduino, and you just need to connect it to your USB, and the LED is basically already starting to blink right away. And you can do all kinds of other things. And I think this is really like the game changer for electronics in terms of rapid prototyping. And everything's open source. I think that's also the key enabler in the end. And luckily, there have been lots of people already doing something very similar for optics. So from well, it looks like a replicate from the Holbein slide, from Bjarne's slide. In fact, it's was there already, but there's a toolbox, or let's say there's an app for that, for all kinds of different purposes. Very recent, so like this squid from the Prakash lab, or the open flexure, which I really liked from the Bowman lab, and also software like Fiji, of course, and ImJoy very recently. So all of these things, they serve you open source hardware and software to really fund your research easily. So you always, well, you never need to start from scratch. You can always build on top of something. And so we thought, okay, there's so much variety in the community. It's all nice, but in the end, we would really like to have some kind of a standard, which I'm always stressing. And if you observe microscopes, of course, well, most of you are familiar, starts with, for example, an illumination, which is eventually then reimaged with a lens, like a condenser. Then you have your object. Object is scattering light, or eventually also fluoresces. And then you have a detecting objective lens, a tube lens, and a camera. And this mechanism here, so you already see that the focal lengths of adjacent lenses follow one another, is called Fourier optics. So you have a Fourier plane, you have an image plane, you have another Fourier plane, you have another image plane. So they really follow consequently each other. And that's nice because this is already inherently modular. And I'm a fan of modules because I love playing with Legos and all these things. And we thought, well, let's just apply this mechanism to optics. And we did that by designing small cubes. And that's the first project I'm presenting you right now. So that's UC2, for those who haven't ever heard of it till now. And so the cool thing about it is once you have kind of a library of cubes, you can stack them together or orient them the way you would like in order to build, for example, a microscope. And this is already directly helpful for the biologist. We presented in the very first slide, because this one here can go into a biosafety lab. It can get dirty because it's all plastic and 3D printed. It's very low cost because it's basically just based on stuff you could buy from any resource like Amazon or eBay without making any advertisement there. And once it's done, eventually it can also be recycled. So that's all what well, the biologists wanted to have in the first place. Well, but if you want to have something a little bit more advanced, for example, like taking videos or having an infinity microscope instead, of course, you can also do that. You can also swap the camera, for example, from a Raspberry Pi and exchange it with your camera from a cell phone. Or even more advanced, you can create a light sheet microscope where you illuminate your sample, as you may know, with a light sheet, like a paper thin sheet from the side, and you detect the fluorescence signal perpendicular to that and create, for example, 3D stacks up from your image and make very nice 3D volume images. Yeah, and so as I said, so we have a library with already existing parts. This is kind of an old thing right now, so that was version 2, which you can also find in the manuscript we recently published. And it's thought the way that the cube itself is always the same, just the stuff which goes in there with always standardized insert, for example, which holds a lens or an LED or whatever. This one can be adapted in order to make a functional cube. And many functional cubes can, for example, lead to a setup. And it's very nice, well, very simple to put together. In this case here, it was magnetically with some ball magnets and some screws. And we basically support all the tools a little bit like this Google Era phone, which was once meant to be used as a module phone and then unfortunately failed in the end. Yeah, so we provide all the tools so that it's really simple to start using it. So for example, if you have a lens from an old binocular lying at home, you can also use this Thingiverse app, which then makes it configurable. So that's well, just give you some ideas. So there can be simple cubes, or also some more advanced, like a Z stage if you want to refocus, or take Z stacks, for example. We also make sure that it's compatible with other open source projects, like I said, the Open Microscope. And very important, if you have an idea and you would like to see that, you can always file an issue in our GitHub repository, and more to that later. And well, now again, so the biologist in our case, in the very beginning, was actually not a girl, it was a boy, and he wanted to observe macrophages, differentiating macrophages from monocytes. And so we designed this very simple microscope based on finely corrected objective lenses and a Raspberry Pi camera. You take the parts from the shelf, which are already pre-printed, and then you assemble it, put some electronics in there, put it into an incubator, and eventually you start the image acquisition, and it lasts for weeks there. So we were really able to observe how these monocytes differentiated in the end, and gave us the idea of what's the challenges there in the end. So incubators are nice for cells, but not really for 3D printing materials. So yeah, more details you can definitely find in the paper. And so one step further, we thought, okay, this is a nice tool not only for biologists, but also if you want to teach, for example, optics. So we took our bags, stuffed some cubes in there, and then we went to different locations and we're teaching Fourier optics, so everything what you probably know from Rainer Heinzmann's lectures. And it became really, really handy to teach, well, what is a Fourier transform, what's a Fourier filter, and how you can use it in order to make some fancy microscope out of it. And so we compiled everything here in a box. So it's really called the box, and we have plenty of boxes now with different titles meant to be used for different institutions, for example, for universities, for schools, and so. And what we tried was always to maintain somehow like a CO2 limited budget when we're traveling. Well, and now since there's Corona, we also had to make sure that this can happen over the air. So now we have well, compiled an online workshop, which we performed already a few times. And it can do basic experiments like a telescope or like simple microscope, but also like a light sheet microscope or a spectrometer and all that stuff. And after printing many, many cubes, well, we found that it's really, really time consuming because one of these cubes, even if you don't print it in the best quality, takes about 2 hours. And if you need 1,000 cubes, just imagine how long that would take. And then the rapid prototyping is actually not the tool of your choice you would like to use in the end. So we decided to go the way of doing injection molding. That means you have a injection mold and you can really fabricate your stuff like Lego is. And then you have much higher precision. So now it looks like this here. It's well, fully compatible. And you have these puzzle-like pieces which you can then connect, which either like infinitely long, and you can really stack stuff together. So that's really nice if you want to make more complicated setups. And so we also have this box. It's not only in the picture, it's also here with me. And we have plenty of these boxes, and we can ship them to different schools and universities now during Corona to teach or to basically maintain this flipped classroom. And Barbara Marsikova made sure that it's really comprehensively done with documentation, and all that is also can be found online. And yeah, so you can do more than just that. Well, since Rainer is very famous for all these super resolution methods, we thought, well, let's just try out whether we can do SIM, for example. Well, there's another very skilled PhD student, Haran, who recently worked very much on this DMD-based structural illumination microscopy, which was, well, originally thought to be part of the symposium. Unfortunately, Corona was also involved here, so we now had to do it here in our lab. And it's really simple. You just have a laser point to a DMD while you do the ordinary Fourier filtering, and in the end, you have a two-beam interference in the sample plane. And that's quite nice. Because then you can increase the resolution by, well, theoretically a factor of 2. I don't want to go too much into the details here right now. Just emphasize that this setup is very similar to another one, which is called image scanning microscopy. So the only difference here, as you may have seen, is that we don't use a DMD, which is a well, 2D display, which can display a binary grating, for example. In this case, it's a MEMS, so it's a micro electrical mirror system, I guess. Oh, I forgot. And it basically deflects laser in this case. And you have 3 different laser wavelengths, for example, RGB, which can excite GFP and LXR647, for example. And then you can create a pattern in the sample plane. And since we thought, okay, they are very similar, and we would like to test both of them, and we had 2 electrical components, both open source, both very reliable, we thought, well, let's combine it and see how this goes. And since we can stack the cubes, we were just stacking layers like onions or orcs. And so you basically have the sample layer, the illumination layer, where you have the SIM part and the ISM part, and the detection layer, so to say. These here are some results from the image scanning microscopy, where you have the points that temporarily moving over a sample, doing the pinholing in the computer, and then eventually getting a higher resolved image. We always try to also process with SURF. It's quite nice from the Henrika group to, if you don't know the illumination pattern and try to, for example, reconstruct fibrous samples like the actin filaments here from a HeLa cell. So in fact, you get a better sectioning compared to white fields, which unfortunately is not shown here, but anyway. So this is the ISM, and the SIM was even better. So here we had some actin labeled HeLa cells with, well, in this case, a kind of better objective lens. So this is not a super fair comparison, but you can, well, using two rotational angles and 4 phases, get a resolution of around 150 nanometer, which I was quite surprised of. And so we meant to be used, well, we thought it's useful for teaching purposes, but I think it can be also used in all kinds of other fields. So the whole setup can be replicated. It's all documented in the paper and also in the GitHub. It's roughly €1,000 for both modalities. Right. So the power in your pocket. So I'm switching to another topic, which is really now taking care of this thing here, their cell phone. And so what we have seen now, fluorescence, was this process where you basically excite a fluorophore. It's sitting there for some time and then eventually relaxes here. But well, now we really tune the laser power to its maximum. And then eventually we can get the effect that it's not emitting directly, but rather, well, staying in some dark state and eventually relaxing back into the ground state after some time. That means that you won't see all fluorophores switched on at the same time, but you rather see this blinking effect. And if you then do some tricks where you then record many frames and you basically localize each of these blinking events here and say, okay, this is my position, and you do that for every of these little dots, and you do that for many frames, then in the end you have a better resolve or a better localized result. And what we try to do is we basically exchange the €20,000 camera with a, well, €20 camera module, well, still in the cell phone, and we try to see how it goes. In this case, it failed completely. It was the first approach where we try to reconstruct something, and you already see that there is a pattern involved here. And this is, well, most likely the compression, we thought. We did some investigation, and yes, it's coming from the compression, from the JPEG compression. This is, well, I don't want to go too much into the details there, but the kernel, or the way it works, it produces hard edges where the ordinary destorm or the storm localization routines just fail. And we thought, okay, well, there's another evidence that basically destroys the localization accuracy. Well, big data, that's the thing we would like to use. If there is something which can translate Google Maps data into aerial images or horses into zebras, well, there must definitely be something which produces good data from bad data. So we trained a neural network. In this case, it's a generative adversarial network again. And cool thing about it was that you can port it to a cell phone. And so then we were able to localize stuff on the cell phone directly. So we called this whole thing CellStorm, and we used, well, in this case, a Huawei camera because it has a monochrome camera. So you collect 4 times more photons in case of Alexa 647, for example, in the red. It was quite nice, and that's the localized results. So you got, with a very heavy microscope and some microtubuli stained HeLa cells, a resolution of less than 80 nanometer. Well, now we were somewhere here, so we replaced this little camera here. But of course, we wanted to go somewhere much smaller. And you see here, there's a left space, and that's the new thing. That's CellStorm 2. And well, it's working completely different. And but at first, I would like to show you this slide here. That's one of my favorites. And I always need to go back. Okay, what's the replacement for a heavy laser? Okay, of course, a small dyed laser, which rapidly can burn your eyes. So take care. or like a cell phone camera for instead of a EMCCD camera. Well, of course, the comparison is not really fair, but in many purposes, it kind of works okay-ish. And so what we built then was we built on top of the feature of these voice-call-driven lenses, which you can also find in your cell phone, like as an autofocusing module, or in a CD and DVD player, which have like a very, very high NA, and you can move them in X and Y in the nanometer scale. And so we thought, okay, we can combine this with something from the group around Bolbert Singh and Øystein Helle in Tromsø University in Norway, and they have these photonic chips. So in fact, it's like a cover slip. It's not made out of glass, it's made out of silicon or some silicon dioxide, and then there's a high reflective material on top. In this case, it's, for example, a slab, some 25 to 500 micrometer thick and 150 nanometer high. So it's insanely small. So it's a fraction of the wavelength. And if you're lucky and couple enough light into this little slit here, you may get the chance that once you let cells grow on top of your waveguide, bring it to the fluorescent state, or if you really have enough intensity and the right cocktail, like the buffer condition, you can bring them into the dark state again. So you can perform D-storm imaging quite nicely because the illumination layer is disconnected from the detection layer. And we thought, okay, so this is already nice, but still we need some 150,000 euro investment for building some device like that. So we said, no, we want to use the CellStorm approach, where we basically came up with this compact design. So you see the cell phone laying on top. There's a very simple mechanism of a finely corrected microscope design. And the coupling mechanism is really just laser, the optical pickup unit directly coupled into the waveguide. And you see here this line here, that's basically the coupled light. The coupling efficiency is surprisingly well, and you can tune it, like as I said, in the 20 to 50 nanometer range with some very simple electronics here. And so, just showing that again. And the first thing, well, D-storm is of course quite sensitive to intensity. So we started with something else. So this is the Aurora Borealis well, I've seen in Tromsø once, kind of, and the same effect, funnily, is taking place in these chips. So they are single mode in one direction. That means only certain wavelengths or like certain waves may be allowed in this little waveguide. And if you move the lens along one direction, the mode pattern, like the interference of the different waves inside this very, very flat channel, they move. And that means that the intensity pattern, similar to structured illumination, also moves. And as you may know that from SOFI or SURF or all these algorithms, you can then, for example, increase entropy in this image. And in the end, we did that using some membrane labeled E. coli. And this is the bright field, and you can really recover the membrane quite nicely without any D-storm. So this is definitely also possible with living cells. And so we pushed this topic a little bit further, and we were able to, well, get by the limitation of the cell phones in terms of camera. So usually all the cameras, they have lots of image processing done on the chip so that you can really make nice photos at night, and you can see people on images quite nicely. But this is, well, a massive problem in scientific imaging, where you really need raw data, so you need to be quantitative. And so we found a way to take images at a reasonable frame rate in a raw imaging space. That means there's no compression, no denoising, no nothing anymore. And we were able to, well, at least do that for these Huawei devices, which unfortunately was not possible, wasn't possible by default. So this is the SURF reconstruction, for example, from a raw data stack. And here from an MP4, you may say, this looks better, but I wouldn't trust the MP4, like the compression algorithm, too much. So in the end, we were able to really well, use the cell phones as a scientific imaging device. And one thing, well, I'm coming to that a little bit later. which is useful, is that most cell phones nowadays, they're insanely performant in terms of computational power. And if you want to use a microscope without laptop or anything, for example, in high safety labs to, for example, detect coronaviruses, you want to do the image processing, of course, also on the same device. And so we came up with the idea to create another neural network. In this case, it's something temporally. So I don't want to go too much into the details here, but the idea was that since the SOFI data, so the structural, the fluctuating intensity data is a temporal stack, we would like to get a higher resolution from that. And so what we did is we trained something it's called a convolutional long short-term memory network, which, for example, expects 100 frames and produces a nice frame as a result, as you may see that here from, that's the mean projection and that's the reconstruction result. And so we're not aiming for a proper super resolution. It's more like a quality check. So just some disclaimer. And here you see some results from these fixed membrane labeled E. coli. And so you can get, this is real time from a screencast, and you can really recover the membrane using this neural network running on the machine. So yeah, it's really impressive how much computational power your cell phone really has, and you probably most of the time just never use it. Yeah, and so as I said, you can also do D-storm, for example, as you can see that here with an actin labeled HeLa cell. You can get resolution in the range of 100 nanometer. With proper labeling, you can also recover the microtubule network quite nice. So you can see that here. So this is also from a time stack where you use photo bleaching as a matter of, well, increasing the lateral resolution, also using surf again. And yeah, here's another example for D-storm on a very, very large field of view. And here you can also get some 100 nanometer resolution. And as I've mentioned, well, roughly a year ago, when we came back from this workshop in Oslo, the pandemic, the corona pandemic really was basically following us. And so there was a lockdown, and I was getting quite upset because I wanted to do something. And then we came up with this idea to eventually detect coronaviruses. So, well, you may know that there are lots of different protocols you can use in order to detect it. Immunostaining is one approach, and we also followed this idea. What you do is you well, in this case, you have a virus sample, you immobilize that on the surface of this chip. Well, you have some antibodies. In this case, we were lucky we had them some at hand very fast, secondary, in order to make it fluorescent. But then, of course, you have the problem that eventually you get also unspecific binding and lots of false signal in the end. Luckily, well, we thought we can do single molecular localization and differentiate between viruses by its size. And also, Pablo and Kai came up with an idea to basically produce pseudoviruses or virus-like particles where we have a fluorescent signal by default and can add our antibodies to test whether there is co-localization or not. And in the end, we had both. So, so we had the signal from the antibody and the size as a, well, specificity factor. So here you can see the coronaviruses we measured. Well, so these are active coronaviruses, and that was quite nice because you can easily measure that with a cell phone, because the cell phone, well, you can just bring it in once. It's in the range of less than €1,000, and then you can do all kinds of things. And of course, it will never leave the lab anymore without damage, but it can stay there and it can do produce nice images. And so now we have the size, so you can really resolve the particle as a roundish particle with some 150 nanometer in size, as at least we think so. And we have the additional measure of colocalization. So here you see the green spots of the virus-like particles expressing M-Sherry and the antibody signal in purple. And on a control group here with some HIV, you only see some artifacts here, which may be very likely due to some dust or something. yeah, and so well, coming to the end more or less, I think this one I may skip into, well, maybe just emphasizing the idea that you have this optical pickup device. It's not only useful for a chip, because you may ask yourself the question, well, where do I get this chip from? And well, there's a good message. You can buy it very soon, but you can also use the setup for example, fibers. So if you have a fiber lying around, and well, if it's a hollow fiber, for example, and you have some particles you can add in there, you can also do scattering measurements with different wavelength, as you can see here. And then it's just a matter of creativity. You can apply that for biological experiments anyway. So, and yeah, it's already quite late. And so this is something, well, I would like to show you. It's not quite done yet, and it's the time is over, but there will be definitely some merge process coming very soon. And also we're working on something, as you can see here, it's meant to be for high throughput stuff. And also we started recording lectures. So together with Manu Prakash from the Foldscope gang, we have worked on some stuff for the frugal science lectures, and we thought, okay, this is very nice, and we would like to push this a little bit more together with Renee and Barbara. And yeah, that's, I think, about it. So just to summarize why open science is so cool, yeah, you can just download stuff. Well, we recently also introduced an online configurator, which makes things so much easier. You can just go shopping, you can just print stuff, assemble it, and then do the experiment, and then you're done and can share the stuff. So, and that's, yeah, basically it. Yeah, so I may give a brief intro into the stuff later in the discussion. And so, recap. So, lessons learned. So, the Chinese resellers are not really reproducible in the sense that you buy stuff once and the second time may be a little bit different. So, for example, the whole position of the XY stages sometimes a little bit different. Also, buying stuff from China, not super easy, because our institute, for example, and I think many other research institutes, they don't like it because, of course, they don't really do the tax billing nice. So we found that it's a learning process for institutes to do this open science path. We did this learning process together with the institute, and everybody in the end was quite happy. So, of course, the intellectual property might be an issue, but I think the institute benefits from visibility quite a lot. And also, I think that's where research should go in the future. So that's definitely something you should keep in mind. Well, documentation takes time, but it's worth the effort for sure. And yeah, so I think all other points I already mentioned, kind of. So, well, going to the public as early as you think is always a good thing. And so far from our experience, nobody took advantage from our stuff. Well, and well, maybe they did, but not that it was a disadvantage from our side. So far, only good experience with openness. Yeah, and so maybe that's then the very last thing. In the end, I hope that you see too. And yeah, there's definitely some openness missing, and I think that's maybe the starting point for the discussion, or maybe the questions. So thank you very much from my side. Also, thank you very much. Well, thanks to the team, and yeah, I hope you're ready for questions, if there are any.
Thanks, Bene, for the excellent talk. So, Stephanie, shall we do the questions and give Bene a break, or we do the Mentimeter? Stephanie.
Myself. Yes, we can do Mentimeter. I already sent the Mentimeter out. I think people are already kind of starting to work it out. So
It's
I think the Mentimeter is in the chat. So I think anyone who wants to play Mentimeter, come on, guys. This time you need to kind of play Mentimeter. It should be fun. All right, I can see some good stuff coming in. So I'm going to do this, and then I'm going to share my screen. So you go. Whee! So you had the first question already? Yay. I like a bit of money, which is good. So as you know, like if you're participating in this amazing Mentimeter quiz event, you can win a Foldscope. So you should be inspired now that everything is possible just with a bit of paper. Okay, we're kind of someone's taking a photograph. Okay. Are you now ready to play? So now everybody has signed in? No screaming? All right. Okay, so this is your first real question. So those are the guys who are playing. And okay, so as faster you answer, as more points you get. I mean, Ben, I can maybe help even with this because it's sometimes hard to make these questions short enough so they fit. But I think this should be quite what enables high SNR nanoscopy using a smartphone in cell storm. And I think having listened to Ben is, okay. More pixels was the kind of easy answer. People want compression algorithms. Those are probably quite a lot of mathematicians in the audience. Image analysis people.
That really is the question I was asking. Okay.
Question 2. So what makes UC2 so modular? So you have 3 answers here. The Fourier optical of 4F principle, the Fresnel propagation, and Huygens principle. Yeah, you're right. So people listened really good for that one, I think. Excellent. You can make some comments, Ben, if you want. And I'm just kind of...
I'm just observing.
It's interesting when you're giving the lectures what people actually learn.
Yeah,
so which optical system is the most difficult to realize?
I'm not quite sure what I had in mind when I was asking the first question. I don't know. SNR, how does it relate to pixel size? I don't know.
All right. Okay. So the spectrometer is the most difficult to realize. Is that right? Did I?
Stephanie, I mean, there can be some errors.
Yeah.
Was it not right? I mean,
everything which is not 90 degrees is kind of difficult. I mean,
okay.
By the time I was asking the question, I think the DMD was not quite done. So now this is also not so complicated anymore.
But Stephanie, this is fun part of our quiz also, right? Like,
where does the
even if you answer all...
So I like this one. Where does the optical pickup unit originally comes from?
Yeah. So Stephanie, I was just saying the great thing about our quiz is even if you don't answer all right questions, you can be a winner.
That's true. Well, I always kind of find it quite funny because it does some kind of word correction, but actually this kind of Mentimeter software just actually sometimes messes up because I copy and paste actually people's text. So, but sometimes I get some very odd corrections, but it's okay. Why can we increase lateral resolution in photonic waveguide chips? I think this is kind of interesting. Oh, do you want to explain this one maybe, Ben? Because I thought it was interesting. Impurities in the material induce spatial varying intensity patterns.
No, I think that it's actually number 1 is correct. So discrete mode field pattern use a temporal varying. So if you take the mode, then you should get this, well, temporally moving pattern, which you can then use for example, Sophie or Surf. So I'm
Oh, maybe I put it the wrong one then. Well, sorry, you can kind of just kind of win by thinking maybe the wrong thing, but never mind. Oh, I need to check this.
I don't know, maybe.
So whoever is Thomas has, for some odd reason, won this quiz. Not so sure it was actually then the correct answer.
This is
sorry, guys. There's an element of randomness in this.
Yeah, well, always.
Okay, so if you're Thomas, if you were kind of...
Congrats, Thomas.
Have I stopped sharing? That's okay. Have I stopped sharing or is sharing?
Stephanie. So now we go on to the questions, and we have a lot of questions actually. I will ask first. Like once I was discussing with Eric Bedzek about all these low cost setups, and he said very less chance that they will be eventually successful for research. Like you can use it in school, colleges, and things like those, but getting research grade results. So towards the end of your talk, you almost convinced at least people who are new to microscopy that they can get very good images and even research grade. So what do you think are the next challenges in this area, to really compete with, let's say, these $2 million, $1 million scopes?
Well, that's in fact a very good question. I think it's it's multifaceted. So I think at first it's a psychological thing. So you really need to convince people that, well, of course, a STEP microscope, I think in a way it has to be expensive because you need complicated optics. I think that's also like everything which is short pulse and so. But many people still connect good quality of images to high prices, I have the feeling. So so it's kind of a private story, but we got some feedback from the Cellstorm, and so they were really claiming that it's not it would not make its way through community, and so I think that's one thing we have to improve, that you can really do crazy science with low-cost stuff. Of course, the effort of assembling and maintaining is higher, but I think assembling a STEP microscope is much more complicated than assembling a Cellstorm. So that's one thing. I think in terms of detectors, of course, we're not there yet. And optics, yeah, they're not really reproducible in the sense that you buy two lenses and they have the exact same aberrations in some limited regime as you would expect it from Nikon, Zeiss, or Olympus or so. But well, low magnification lenses, they are typically quite well. So for example, what you usually find in the open fraction microscopes, you can get the same lens from different resellers and they always have the same specs. So yeah, and also lasers, it's a limitation due to available wavelengths. So you cannot find a good 561 laser, for example, which you may use for, I don't know, some crazy dice. But yeah, that's maybe limitation.
Yeah, excellent answer. And I especially like the psychological part that, people think unless it costs $1 million, it won't give me a good image. And whatever the $1 million throws up, people just blindly believe it, right? It's a great image without even going for some more validation. So I think it's a very important point, and also the mindset the science community has gone into. I will take the next question. So what guys we also do is, if you want to ask your question yourself, unmute yourself and ask directly. It will have some variety and some new elements. So Amir Ali, if you want to ask your question, else I will go ahead. The next in line is David Lee, and then we have Alexandro, William, and Richard, and then yeah. So I will take the question from Amir Ali. I think Kate, everyone can somehow show the video and unmute themselves, right? If I understand. So
Yeah.
yeah, so yeah, you can do that. So I will take the first from Amirali, and so she or he asked, like, maybe I missed the point. Do you install the setup for clients? I think it's so easy that you should do it yourself, right? UC2 setup, I guess she meant.
Yeah, so we have a number of setups now spread around the world, and so so one thing we nowadays do is like video, video, how you call that, Zoom meeting, whatever, to do the last mile. So we really take lots of effort into documentation. So I don't know, I want to at least give a live demo quickly. So if you were keen on, for example, replicating whatever microscope, so you can go, for example, to our webpage. It's UC2-JIT, and the bio-nano imaging. I think it's the fastest way is anyway to go to uc2.org. Well, the page has been hijacked, so we will be directly redirected to this thing here. And so if you want to replicate, for example, the Incubator Microscope, which is, I think, one of the simpler ones. You can go here, you find everything you need, and then really can download, buy stuff, and so. And then there's a detailed documentation, for example, on how to build the camera cube, for example. And so then there's a picture for every step, and we really try to convince people to do it on their own. And one thing which was quite a challenge with the files and the versionings and stuff, the group from Richard Bowman, which is well, very inspiring with their work, provides this very nice configurator, and we adapted that here, where you, for example, do, okay, I want to build this incubator microscope, and directly it gives you all the files, you can download it and then just print it. So I think in the end, that's maybe also a challenge for open source, open science, whatever. You really need to make it that simple that people can just grab it and do it without, okay, I need to read 20 pages of documentation and then start here, there, no. So it needs to be very, very simple, and then always be open. So in case people have questions, you can go through the issues with them together. So that's what we do now. So clients, if you say that's people who use it, they will do that themselves. And if they have problems, they can always file issues or contact us. If that's the question, I hope.
Maybe, Bene, we can also do a shameless advertising of symposium for at least people in the UK. So possibly, given COVID, we might have whole UC2 workshop during a conference on structured illumination microscopy. We are planning to have it later this year. And Bene will be doing like 2 days sessions, and he has some very extensive plans to make teams and do some small hackathons. So that might happen. So if you are in UK, please do come, and we have some funding for it from Zeiss, I guess, to build a few of these UC2 setups.
Yes.
So yeah,
all this there. It's just COVID is also there. That's a problem.
but we are very motivated to do a hands-on on-site workshop. And Stephanie, Lothar Schimmerle, Rainer Heinzmann are other co-organizers. So yeah, please register. And I think we have around 100, 200 seats for it, and all is free, like registration and everything. So the next question, yeah, anyone was saying?
No, I mean, on this question, I just want to mention, I think, I mean, I wouldn't really put in competition, let's say, this project or similar projects that are completely supportive of open science with actually commercial companies. I mean, from the question was a little bit implied, maybe you, Benedict, also implied it in your talk a little bit, that this would be the case. But I guess that, you know, when a company is selling a microscope, of course, they provide the service, application specialist, and they use the best quality product usually. So it's a little bit like wine, if you want, you know, the more expensive the wine, actually, up to a certain point, it's true that it might be better but over a certain threshold is not true anymore, you know, because it is the brand and so on. So I would say that that is one aspect. So that I don't think the two things are in competition, and I do believe that great commercial systems or great prototyped systems in a lab that with expert will be always, you know, performing in excess of open science project. Now it is up to the individual to evaluate if that excess is worth the money or the trouble. The second aspect I completely forgot, so maybe you want to do the first comment, the comment on the first.
Yeah. Well, how could I step in? So one thing. So commercialization, or complicated word. It's not a no-go at all. I think it's mandatory. Also, so we are thinking about it to somehow commercialize our stuff here in order to really make it available. Because the problem is that, well, coming back to the question of clients, the number of people really eager to test it out at home, it's not the vast majority. So you really have to have a 3D printer, you have to have all the skills in order to make it. There's so much stuff which will go wrong, definitely. So if you have something, oh, I take it out of the box, I put it together, and I have a microscope, that would be so much cooler, so that you really have like something which you can use. And I think there's, so maybe that's what you meant, that's where companies jump in. So they really, well, bring it from an okay-ish working state in science or research to something which is working like always, and then you have to pay a price which is then of course higher, because, well, then this ratio of well, the good wine won't give you a headache, whereas a low-cost wine eventually is very painful. So maybe the analogy there is quite similar.
Then what I would ask is, Alexandro, to you also, is do we have a, like, let's say a middle ground between that? Like, are you aiming, let's say you mentioned you put a price tag of £1,000, right, on this UC2 setups. So do you think like we can get a research grade under starting with $10,000 and then slowly bringing it down, and you can commercialize it, right? Like make like put slightly better these cameras, I think 500 or something, and then you can come up with $5,000 or $10,000, something which is as good as research grade, right? And then you are eventually bringing the whole price down slowly. So
yeah, so that's also maybe a process which is heavily underestimated. Like this one slide I showed you with the alternatives for cutting edge research grade instruments, that you really find the instruments which can replace high grade stuff with good quality for a low price. For example, there has been lots of research been done on industry grade CMOS versus EMCCD or SCMOS cameras for single molecular localization. And so I think there is a good quality alternative for most of this stuff, but you really need to find it in the end.
Alexander, my question to you would be slightly like, you know, we have a confocal at £500,000. Then let's say we have a STED at £1 million, and then we have a Minflux at 2 million. So how these 4 or 5 companies have priced it, you know, with resolution, almost implying higher standards, right? And then you always go a fold more in the price, even if the optics is the same, you know. It costs like 10,000 or 20,000 or 50,000 max. It's just the, so I think like, isn't there a big market for, you know, research grade, high standard instruments within $20,000 basically? So Bene, instead of this $20 camera, you can put a 500 ILR camera, which is very good.
It is already happening. I mean, when you commercialize things, then there are a lot of overheads that when you do things as an open science project, you don't have. And actually, by the way, pay attention, I'm not criticizing anything. I'm actually fully supportive. I'm only saying that the difference of price is because of many different things. And just for example, if I build a system by myself, I don't pay royalties. And, you know, I don't have to make a profit. I don't have to pay the pension of my employees. So, is
totally. I mean, I think we're in a lucky position that I don't need to worry about the end of the month. So I just get money. And I'm also lucky that Rainer supports our research here and that it's quite accepted right now. I don't know how this will change. But so there's also a movement towards like this open source-ish product thing. So, I mean, Richard's group is showing that how well this works. And also this OpenTrons, if you haven't ever heard of it, it's an open source pipetting robot. And also Arduino and lots of other things which follow this open hardware idea. I think maybe they pave the way for some more of these projects. And I think what you pay for in the end is also the service. So if you pay, say, $1 million for STAT microscopes, well, then there has been many iterations of development cycles where many people work together to make everything work with a button click in the end. I think there we are not there yet. And I think Richard Bowman's group, they really push this topic to a very large extent where people really get a nice product, but in fact, it's a research grade or a research project. And I think that's a very good role model there.
And I would just like conclude and move on to another question. Is like, like let's say confocal is $500,000, right? So the service for confocal would be same as for like there is a STED module on top of it. So I don't think there will be more like, men involved or people involved or more service involved. It's the same infrastructure. It's just like you're charging twice of what a confocal from Leica would do, right? And then you have a STED module on top. So I don't think there's more service in that. But I think we are going on one specific topic. So next question is from David Lee. So he talks about training GANs and real-time processing. David, you want to ask your question, or I can see you? You are here. So okay, maybe not. So so he asked.
Excuse me.
Yeah, go ahead.
Yeah, I'm just interested about training. Of course, the training is not done on the mobile phone, but when you implement the train network, do you do it in real time on cell phone?
Yeah, so that's why I wanted to show some demo. So the project page of this CellStorm 2, well, it's a long URL, but there you can also find all the software. I think there might be also the Google Colab network thingy eventually. Yeah, so the network and everything you will find online. Whatever. So what's important is you can try that in the browser. So there's InJoy, that's from Wei Wang, who has this super cool image processing tool which runs in well, in your browser basically. I don't want to go too much into the details, but you can use it for example, ImageJ. And so he, well, compiled the TensorFlow model, which originally runs in the cell phone, to this ImageJ plugin. So here you can find some stack as an example, 30 frames. And you can then call this plugin. So it's a pre-trained network. And then you just apply that to the stack. And it runs through the stack in your browser. So you can also do that on your cell phone. And then in the end, you get a kind of super resolved result. So this is maybe not quite fair. But since the network is probably not the best one here. But what I showed you in the slides, that's real time. So you get a snippet of your frame with 256 times 256 pixels updated every second. So you have roughly 1 FPS, like 1 frames per second, with a cell-stormed result. So if you want to read more about it, I think I can just highly recommend you to go to this webpage. I can probably put that into the chat, and then you can go through it. And also cool, you can do lots of image processing on the cell phone itself. So for example, autofocusing, or you also have this auto coupling mechanism. Everything runs on the cell phone. So yeah, I hear this. So there's must be some collab thing. Yeah, somewhere here. I posted in the chat.
Okay, thank you.
Sure.
Next question is from Alexandra. You want to ask? So it's yeah, injection.
Just I was
molding.
curious about injection molding is something you do in the lab. I mean, is this by the way, it's not related to cost. Don't misunderstand. Is it something that is affordable from an average lab that is doing prototyping?
So as I said, so we really had to manufacture 1,000 of these cubes because we wanted to support a workshop with students, which was supposed to happen last year. And then we thought, maybe that's a nice idea to well, write a grant application, and we got the money, and then we went to a company producing it eventually. So we have now really like 1,000 of these cubes here, so you can create arbitrary complex systems like this pyrography system. But since we only have 1,000 and one of these molds costs like 10,000 and we have 2 of them, it's getting quite expensive if you do small scale things. The more you order, the more you'll get. So, and right now it's just research, but it's done by a professional company.
And can give you a feeling about the price.
Yeah, so well, one of these tubes here is like 20 euro plus one of these base plates, a little bit more.
Okay, thank you.
Mm-hmm.
So next is William Gang. You want to ask, it's actually a simple question, how you do turf alignment, or how long or turf alignment is for Cellstrom?
Well, there are 2 questions. One is written in the manuscript. So as I said, so I maybe can share the screen again quickly. So there's an auto alignment feature in the Cellstorm app. And it works by basically maximizing the intensity you see on the screen. So either scattering or fluorescence. That's how the Cellstorm works. So you can also do, for example, long time series. So we did one overnight series from HeLa cells, but they unfortunately didn't survive that long. I think that's the one I didn't show. Yeah, so this one, for example, was overnight. So there's no drift or minimal drift, and also no coupling loss involved, because we do recoupling and autofocusing periodically. There's a new approach I'm working on right now, which works very, very good without any scattering or fluorescence signal you need to detect through your microscope. This is something I will most likely show maybe in a month or so. So I can tell you more about it once it really works.
So next question is from Richard. Richard, you want to ask?
Sure, thanks. I was curious during the quiz if Benedict's correct answer suggested that he was confident that UC2 assemblies were stable to better than a wavelength. I think 3D printed interferometers is something that I've played with a bit in my group, and we found it surprisingly hard to make it work. Not necessarily just statically sitting there and being stable to one wavelength, but being able to get any degree of controlled motion without your fringes just going all over the place is the really hard part.
Yeah.
I was just curious if you had experience of that.
I'm not quite sure whether I showed this slide there. So we have done one brief experiment, at least it's in the slide somewhere, I guess. So we just built a microscopic interferometer to show the difference between the injection molded and 3D printed parts. Surprisingly, both of them were quite okay. So that's like, is it over? No, that's just 1 hour. So, but the problem we saw in the end is that the interference, well, the contrast was basically ruined by the laser. So we had a laser pointer, single mode green, so the frequency doubled, but there was something weird happening with the modes which came out there. So I don't know. So it's hard. Well, we didn't really quantitatively go into that too much. But I think if you, for example, want to control motion linearly, you can really nicely use these voice call motors from CD drives. So they are usually quite linear with this tilting, but for mirrors it shouldn't matter too much, if this is what you meant.
Yeah, okay. No, that's an interesting actuator to play with. I've not played with the voice coils.
Yeah.
I've never figured out how to do the drive electronics side of that, but I should probably look at your documentation.
It's really just PWM with some LED buck driver. So
oh, cool.
Nothing more. Yeah. And ESPs work better than Arduinos because they have higher carrier frequencies.
Thanks.
Sure.
So, Ben, the next question is from Jia Zhao. Do you want to ask yourself? It's my favorite question, actually. Zia Zhao.
Yeah, hello, Benedict. And here's my question. And I'm curious about can you use the UC2 to realize the stat microscopy? I think, and the stat is used a highly coherent light source. And how to deal with it, because if you use the LED, it has a low power and the coherence is not very good. So is there any possibility to overcome these drawbacks? Thank you.
That's a good question, and I'm sure many people are interested in having a low-cost stat. So I'm not really that familiar with the realization of stat, but I'm assuming that you really need to have very well aligned lasers, since you need the excitation and depletion beam somewhat well coinciding in one place. I think you need also short pulses, right? And probably also very good coherence. So coherence in general is not such a big issue when it comes to laser diodes. For example, frequency doubled, like this 532 nanometer diodes, they have very good beam profile. Also some of the 635 nanometer laser diodes, they're quite good. But I think pushing it down to some state where it's stable for more than one experiment, it's quite challenging. Also, since the laser sources you would need, I expect they are not really easy to get. I've never seen anything on eBay like that.
Yeah.
But I think to visualize the principle, of course, you can maybe create a phase mask with an SLM from some projector or so, and then go for it. I don't know. I haven't thought about it too much. Maybe worth a try. But
yeah, okay.
Confocal works.
Yeah.
Thanks.
I think we are already quite a bit over time, so it's a good time. Thanks everyone for joining, and yeah, Ben, it was an excellent talk. Thoroughly enjoyed it.
Thanks a lot.
Yes, it was super. Thank you very much. Congratulations.
Yeah, thanks.
It's just inspiring so many people to do new cool stuff. I mean, it's wonderful. Really, really beautiful.
That's the contribution.
Thank you. Yeah, no, just kind of disruptive technology. I think it's not